Hi everyone, my name is Giacomo Barbieri and today I'm here to present you this work called an FMEA-based methodology for the development of control software reliable to hardware failures. I'm an assistant professor at the University of Los Andes, and this work was in collaboration with the Universidad Federal de Rio Grande do Sul in Brazil. So we will start with an introduction, then we will present the proposed FMEA-based methodology, and then we will apply it to a case study for its validation, and eventually we will finish with a result in discussion and conclusion and future work. So as introduction, we have that control software must be enhanced more and more with functionality for handling failures in hardware components. We have different methodologies that have mainly focused on the design of software as a means to satisfy functional requirement in automation system. However, there is the lack of approaches concerning the development of functionalities for the detection and management of hardware failures. The inclusion of functionalities for the detection and management of hardware failure within the control software requires an interdisciplinary approach to the designator of the problem that merge hardware and software component and verification techniques able to check the behavior of the control software in response to hardware failure. With the objective to bridge this gap, in this paper, we propose a methodology that combines a hardware failure analysis process, a modeling tool tailored for automation system, and a verification method consisting of virtual commissioning and fault injection. FMEA, so failure mode and defect analysis, was selecting and is a process of review the maintainable items of physical asset to identify potential failure modes and their causes and effects. And this is selected for the identification of hardware failure and for the definition of strategies for their management. Whereas automation ML is fundamental to represent all the different views of automation system and their interrelationship, since it is able to integrate mechanical, electrical, and software views and all their interrelationship, and is selected to gather and sort out the information needed for the FMEA analysis. Eventually, virtual commissioning consists in a verification strategy performed by interfacing a discrete event behavior model of the physical plant to the hardware or emulated controller which contain the control software to be validated. Finally, fault injection is the system verification bar for forcing, making it the system enter failure states. So at the end, by injecting faults and analyzing the system reaction through virtual commissioning simulation, the reliability of the control software to hardware failures can be verified. For reliable, we mean a control software able to detect hardware failure and able to mitigate or eliminate the effects of the detected failure. So our methodologies consist in 8 phases that we will see directly applied to a case study for better understanding it. And this means to be applied to an already designed operating automation system in which the control software must be enhanced with functionalities for the detection and management of hardware failures. So the case study in which we will apply the methodology is an hydroponic test bench, which is contained within the Laboratory of Controlled Environment Agriculture at the University of Los Andes. And in particular, we will study the filtration unit, which contains an inverse osmosis filter for reducing the water, chloride, and total suspended solid content. Digital level sensors are utilized to detect the state of the system, and a solenoid valve and a pump to respectively input tap water and provide the necessary pressure to make the filter properly work. We can notice here the electrovalve. We can notice here the electrovalve. Sorry, I cannot annotate. So now we start with the methodology. And the first step is the information gathering. So the idea is to gather all information necessary for the FMEA analysis and for the subsequent system modification. And it's important to consider that when we do this operation, that systems are composed as assemblies of components, components and have properties and interfaces, and components of automation systems are characterized with mechanical, electrical, and software view. In particular, if we look at a system view, we can have a mechanical view that is a CAD drawing, software view, PLC code, electrical view, electrical drawing, PID diagram. Whereas at the component level, we have a mechanical view, which corresponds to the geometry, material of the element, electrical view, the supplied power, and the software view, for example, the associated software variable. Then we, after the gathering of information, we have the modeling in automation ML. The information is integrated and organized to generate a complete representation of the system. We can notice on the right the hierarchical representation that can be built with automation ML, and also the interrelationship that can be created between the interfaces of the different components. And then components can be built with custom properties and interfaces. So we use these properties to, for example, set all the interfaces, both mechanical, electrical, and software, and the properties of a certain component. Then we propose to start with FMEA analysis. In this case, the FMEA consists in a failure mode analysis that has the objective to identify the specific manner by which a failure occurs in the hardware of the system, the effects and severity of the identified failure modes, and the action to mitigate or eliminate the failure. So you can see that we build for each maintainable item, we identify the failure modes, and from the failure mode, all the effect also classified for severity based on the consequence of the failure, and then some action that could be done when the failure mode occurs. Then we have the key part of this methodology, that is the FMEA synthesis, in which we have that starting from a maintainable item, we can have a more basically failure. We can group all the different, let's say, failure modes in a failure mode set, since different failure modes may be detected with the same method. This failure mode set consists in grouping failure mode based on the detection method. So if here we can notice that we have the same effect, and so these failure modes would be grouped in a unique set of failure modes. And then we have, starting from the failure mode set, we can identify the detection method, which, starting from the generated effect, detection methods are defined by comparing the nominal and exceptional behavior of selected control variable. When performing this operation, it must be considered that the nominal behavior is independent from the system operational condition. So we can see here that we group failure mode in failure mode sets. Then we identify some method to detect it, and by identifying the nominal and the exceptional behavior. And then we have at the end the identification of a management strategy. So based on the severity of the generated effect, strategy to mitigate or eliminate the effect of the considered failure modes is identified. For example, alarm, warning activation, switch of actuators, etc. Then we have the elicitation. Starting from the result of the FMEA synthesis, we have an elicitation of requirement and a modification of the system. So the FMEA synthesis table is converted into a requirement for the detection and management of hardware failure for the control software. And the system is possible that need to be modified. So additional sensors should be placed sometimes to detect the failures, some actuators, or some additional control software for the detection, or for example, in the HMI for the signal of alarms. Then eventually we have the virtual verification, in which here we propose the integration of virtual commissioning and fault detection. So in our case, what we built was a software in the loop simulation built by integrating a Simulink kinematic model of the filter unit with the Codesys PLC programming environment, and we add some button and gauges to basically inject faults and study the software reaction to them. And eventually, the control software is deployed once its modification and integration of the additional sensors and actuators have been verified through the described virtual environment. In our case, we just arrived until the virtual verification. So as a result, we have that the automation ML really was a really useful tool for the FMEA analysis, since we were able to represent all the different interfaces and properties of the components, and we know that a lot of failures occurs in the interfaces. If we compare the original requirement of the system and the final one, we had an increment of 40% in the requirement. Then, with respect to the virtual verification, we implemented some test cases in order to verify the new software. And eventually, a side effect of this was the building of a maintenance plan, in which basically through the FMEA analysis, we were also able to identify times to preventive maintenance, so to have some inspection and some action on the different components. What we haven't done yet is working on the scalability. So up to now, we haven't basically applied this methodology we apply it just to a very simple case study of a laboratory, of a module of a laboratory. In order to validate this methodology, we should apply it to a more, let's say, industrial and realistic case study. So as conclusion and future work, we have that the objective of this research work was to explore the role of FMEA, automation ML, virtual commissioning, and fault injection for the generation of control software reliable to a hardware failures. By integrating this tool, an FMEA-based methodology was proposed and applied to a case study of a water filtration unit to be validated. The result were promising in the sense that we were able to increment of 40% the number of requirements by adding functionality for the detection and management of hardware failures. However, we needed to better validate this methodology and apply it to an industrial case study. So effectively, as future work, what we identify is, from one side, we have that different failure modes are detected with the same method. And this happens when we build this failure mode set. So what should be done is to identify some techniques with maybe additional sensor and so on, to identify the failure mode that is responsible for the alarm generation. Then we have a very common problem in automation. It's also the problem we have different alarms that sometimes trigger after the occurrence of a certain abnormal behavior. So the identification of the root alarm, so the alarm which is responsible for the triggering of all the subsequent alarm, should be identified. And eventually, we need, let's say, to study this methodology both on the deployment, since we didn't deploy the methodology, we just validate the control code on a virtual environment, and also to apply it in an industrial case study in order to see how scalable is the methodology, so how is applicable to an industrial case study. So this was all. I will be available to answer some questions or to receive some suggestions. And if you want further details, you can read also the paper. Thank you very much. Bye.